Logic. Isn't maths all about numbers? Is what you may be thinking right now. But after a few years of undergraduate study, I can say that this is definitely a false statement. Speaking of statements, logic in mathematics is all about mathematical statements and whether they are true or false. This is called the truth value of the statement. While statements 3x equals 9 or numbers are cool aren't mathematical statements because they aren't always true or always false. Valid statements could be 2 squared equals 4 or the integral of sine x dx equals sine x. Notice that a statement doesn't have to be true, and even complete nonsense such as all pink elephants have 7 legs is a mathematical statement. Another note is that mathematical statements can't be questions. So for example, is Boris Johnson a hunk is not a statement, and therefore not a mathematical statement. Single statements by themselves are not particularly interesting. What we are interested in is how they can be linked as compound statements. For example, consider the statement 1 equals 1 or 6 is prime. This is clearly a true statement since 1 equals 1 is true, but it's a combination of two smaller statements known as operands, namely 1 equals 1 and 6 is prime, linked by OR. The technical name for this OR is a disjunction, but that name is usually unnecessary and you can just say OR most of the time. Now it may not seem logical, but in fact we take an OR statement to be true if both the operands are true. So 1 equals 1 or 2 equals 2 is still a true statement even though both are true. While strange, it's just the convention. Summarizing, an OR statement is only true whenever at least one of the operands is true. Equivalently, an OR statement is only false if both operands are false and is otherwise true. It should be no surprise that AND is also a logical connective, and an AND statement is true only if both operands are true. Its technical name is conjunction, and though it may seem at first glance that OR and AND are opposite, this isn't the case, as true or true is the same as true and true, namely true. But what does opposite really mean for statements? This introduces the last basic operation, not. If you have any statement, the not version, called the negation, is also a statement and has the opposite truth value. For example, 1 equals 1 has the negation 1 not equal to 1. Pretty simple, right? Some statements can get very long, so it is often useful to shorten them. From now, I let P and Q represent any two statements to avoid writing enormous lines. If a statement is true, we say its truth value is T, or 1, sometimes. We also can write T or 1 just to mean a true statement. Likewise, a false statement's truth value is F or 0, and we can write F or 0 to mean any false statement. I'll use T and F from now on. The connectives OR, AND, and NOT are written as this V called vel, this upside down V called a wedge, and this undescribable shape which is just called the negation sign, respectively. So we could write P or Q in this way, or we could write not P or Q and P in this way, using brackets as usual, so we do the thing in the brackets first, just like with numbers. The truth value of these compound statements depends entirely on the truth value of its operands, and there needn't only be two different statements. If R is also a statement, then P and Q and R is also a statement. Note that we don't need brackets because P and Q and R is the same as P and Q and R, just in basic English terms. So no distinction is needed between the two. You can show similarly that P or Q or R doesn't need any brackets either. For any compound statement we can construct its truth table, table that tells us the truth value of the statement for any combination of truth values of its operands. Here is the truth table for P and Q, for example, along with the truth table for not P or Q. Note that we read across each row which contains the truth values of the operands and the truth value of the statement, which is always on the right, and that we can construct new columns as necessary to make it easier to compute the truth value of the statement. Note that, like with numbers and their operations, there is an order of precedence, with not having higher precedence than or and, which have equal precedence, so brackets are always needed when combining or and in any way. Immediately from the truth table we can see that not P or Q is a false statement only when P is true and Q is false, and is otherwise true. Two statements are called equivalent if their truth table columns are identical, which corresponds to the weird equals with inverted commas I've been using. The symbol for equivalence is this kind of triple equals sign. Using truth tables we can show for any statement P that not P is equivalent to P, P or P is equivalent to P, P or not P is equivalent to true, P and P is equivalent to P, P and not P is equivalent to false, P or true is equivalent to true, P or false is equivalent to P, P and true is equivalent to P, and P and false is equivalent to false. These are all really simple and intuitive, so I won't really go into detail about them, but you should think about why all of them are true yourself. The following equivalences are more complicated but often more useful than those before. Firstly, we have that for any P, Q and R, three statements, the following two equivalences hold. These are called the distributive laws, and they're basically the same as the distributive law for numbers of multiplication over addition. This is probably the easiest way to remember it. It's certainly how I do. These two here are called the absorption laws, and you can see that this makes sense because the bracket on the right is completely absorbed by P. Lastly, we have these two, and these are called the De Morgan's laws, and they are often the most used when it comes to actually having to write logic and proof and whatnot during my degree. The prior laws can be used to prove statements are equivalent without using truth tables, which can be useful because the number of rows of a truth table is going to be 2 to the power of the number of operands, and you may have 4, 5 or more, and that 2 to the power of a number is going to get pretty big pretty fast. Let's try an example. Show that P or not P or Q is equivalent to P or not Q. As always, you start out by writing the thing on the left, and you want to get to the thing on the right. A hint for the first step is that we can see that there's a P or on the left of both, whereas it's the thing on the right of the or that has changed. So we may want to start by playing with the thing on the right. I'll fill in the rest of the steps now. You should see if you can identify the equivalents used in each step. If you can, then good job, you've understood it well. That wraps up this brief intro to logic. You can move on to the test, or other videos, or just take a break. Thanks for watching.